So we are now in the second lecture of week 7. So this will be the 13th because remember we missed one due to a quiz. So this is lecture number 13, and we are going to continue from where we left off, which was somewhere in the book. That much I do remember. Let's share the screen. So I don't think we were on chapter 17, but I think we finished chapter 16, did we not? Oh, what did I just press? Confidence levels. Did we finish confidence intervals yet? No? Yes? I forgot. Fantastic. April Montez says, I think so. No, that's a question. I think so? It's more the inflection. I think so. Yeah, I think we do a quick review. We can definitely do a quick review. Let's do the quick review right now. Give me 1 second to load something up here, and then we will do the quick review. So, like one problem for confidence intervals. Okay, so let's share my screen. Let's go back to chapter 16, and let's do confidence. Let's check your skill. That's a good, okay, let's do that. Okay, let's do this one right here. It says, use the following information for exercises 16.12 through 16.14. A laboratory scale is known to have a standard deviation of sigma equals 0.001 grams in repeated weighings. Scale readings in repeated weighings are normally distributed with mean equal to the true weight of the specimen. 3 weighings of a specimen of the scale are 3.412, 3.416, and 3.414 grams. Question 16.12, a 95% confidence interval for the true weight of the specimen is what? So we're looking for a 95% confidence interval for the true weight of this specimen. Who here has any recollection of what we did to solve a problem like this? Even a vague recollection, even if it's not 100%, I mean, ideally it is 100%, but even if it's not, who here has a vague? Let's see, someone, how do I load that up?
Can I give it a shot?
Yeah, whoever you are, sure. Just because I can't see names, so I don't know who's talking.
So the estimate, oh, yeah, it's me. So the estimate would be in our equation, x plus or minus z star times sigma over the square root of n being the number of weighings that we've had. The right side of the problem with the z, the sigma, and the n is the let's see, margin of error. So we'll plug in the sigma, the number of times weighed, and I'm trying to remember the z star. Oh, the z star is the point at which 95% of the graph is to the left of this x value, which is z star. Is that correct?
Not exactly, but I like where you're going, so keep going.
Okay.
I mean, you're certainly in the right ballpark.
Plugging it in.
You're certainly in the right ballpark, which I like. Not 100%, but a lot of what you say is good. So let me just make a few corrections. So the first one is you call this x, but it's not x, it's x bar. And
okay.
That's very important because x bar is the sample average, the sample mean. So it's very important to know the sample mean. So my 3 weighings are 3.412, 3.416, and 3.414. So from that, what is my sample mean going to be? How do I take those and calculate the sample mean from them?
3.414. It's directly in between.
It's directly in between.
Well, it's directly between 12 and 16. It's easy.
right? So in this case, if I add them up and divide by 3, it is pretty basic. Of course, in this case, hopefully it's fairly straightforward. Why? This is 3.414 plus or minus. So we need z star, we need sigma, and we need the square root of n. So some of it I can put in already. I can do that. Do I have n here?
Yes, that would be 3.
So n is 3, right? N is the number of trials. There's 3 of them. Do I have sigma?
Yeah, that would be 0.001.
That's 0.001. They gave me that. They were so sweet. And then the question is, do I have z star?
No.
Well, I kind of do and I kind of don't. The reason why
Is it zero?
Go ahead.
Is it 0.05?
No,
Okay, never mind.
but good guess. 95% confidence, right? Let's go back a second to
1.960.
thank you. 95% confidence, z star 1.960.
And isn't it always 1.960?
Every time the confidence level is 95%, it's always 1.960. If it was 90%, it will be 1.645. If it was 99%, it will be, can anyone guess? Don't try too hard. Anyone?
It'll be 2.576.
2.576. Now, last time we went over why these numbers are the way they are. So let's recap for the 95% case, and that's just our example. By the way, this is going to be 1.96. Just to keep it separate. Just keep it separate. Let me redo the last one. So the reason why it's 1.96 can be seen from this diagram right here. We want 95% to be in the middle, which means how much do I want in this whitish section?
2.5.
2.5%, right? In here, I want 2.5%. Correct? All right, Eduardo, thank you. Which means to the left of z star is how much? What percent is to the left of z star?
2.
Well, 2.5% is to the right of z star, but how much is to the left of z star?
Would it be
It's
97.5?
97.5%, right? So if I were to go to a z table, and then do, so like the first one here, any one of them here, let me clear this stuff, clear. If I were to go, let's say this one right here, the z table, and I'm looking for the area to the left of my number to be 97.5%, then I go right here to 0.9750. And 0.9750 I see is the confluence of 1.9 and then the next digit 6, which is why the C star for 95% is 1.96. Right? So it's a two-step process where you first recognize that we're looking for more than 95%. We're looking for 97.5%. And then you go to your table and you find that for 97.5%, we get 1.96. 1.96. Can you do this?
So if the
problem in the
can
website?
I ask a question?
Yeah, go ahead.
So if the confidence level isn't like either 95, 99, or 90, do we like say if it was 93, would we have to look it up on the Z table?
Yes. So if it's
And
90,
then that would be the number.
that's right. So if
that
it
we
was 90 exactly. So if it was 93%, that would mean that I have 7% left over, which means I have 3.5% here. So it will be 96.5%. And then I would go to 0.965. And that would be about 1.81. So if it was 90, what did you use? 93%, you said? I forgot whatever it was you used.
Yeah, 93.
I would get my Z star for that case would be 1.81. Make sense?
Yes, thank you.
Now, you're welcome. Now, someone said, can I do it on Crunch It? Other than Crunch It. Other than, oh, because you don't have access to Crunch It. So let's take a look. What's my data again? Let's find a look. Okay, so let's do, how do I do this? This would be, this would be confidence intervals calculator. Let's see, look. So confidence interval calculator. How many in sample? We had 3. Sample mean, that was, what was the sample mean? 26.414 or something? Anyone remember?
Wasn't like 2.414
Yeah, there it is.
Or-
Yes,
3.414.
3.414. So where's my 3.414? Deviation was, I think, 0.001. Confidence level was 95%. And so there it is. 3.414 plus or minus 0.00113. Right? So that was just the first Google link that I can find. Does that make sense? I hope so. Now, suppose you want to make a 99% confidence interval instead of a 95% confidence interval. You weren't happy with 95%, so you want to go up to 99%. If you want to go up to 99% confidence, then what would happen to the margin of error? Think about that one. So someone said greater than the margin of error. Does anyone else want to venture either a reinforcing opinion or a different opinion?
I'll say lesser because it's getting closer to the true meaning.
So it's important to realize that what the number for the confidence level is representing. You ever play basketball or watch people play basketball? I hope so, right? The NBA finals are tomorrow. Go Lakers. Anyways, or not tomorrow, Friday. Yeah, tomorrow. Anyways, if I shoot a ball, depending on your skill, you have a certain likelihood that the ball is going to go into the basket, correct? If I want to be more confident that the ball goes in, do I want to make a smaller basket or do I want to make a bigger basket? If you want to be more confident that it went in, you make a bigger basket, right? The bigger than that, the bigger the basket, the more likely it is that the ball's going to go in, correct? Right? So it's the same idea here. The confidence is how confident you are that your interval has caught the true value. If you want to be more confident that you caught the true value, then make your interval bigger. The bigger your interval is, the more likely it is that you caught the true value. So if I go from 95% confident to 99% confident, I'm going to have a larger margin of error. Of course, in this case, if you actually do the math, because sigma is so small, it doesn't go up by much. So it really is also about the same. I mean, it's bigger, but it's about the same. Let's see which they want. Okay, so they say bigger, but it really is almost exactly the same. I mean, it goes up. I did the math earlier. It goes up in the 10,000th place. I mean, it's such a small difference that, and it's really about the same, but technically it is bigger. So do this one now. We're still using the same sigma as before, but now we're weighing a different specimen. And in this case, they do not give us the actual data like they did in the last example. In this case, they give us just the summary. They tell you that the average weight was 4.1602 grams. And they want you to compute a 99% confidence interval for this sample. So how would I do that? Someone else walk me through the steps for at least the math for what the equation would be, not the equation, what the expression would be for the confidence interval. What would I write?
You would put 4.1602 for the mean.
Okay, 4.1602 for the mean. Excellent.
And then wouldn't it be the square root?
Well, the square, it's in there somewhere, but let's go in order. What comes next?
Oh, plus, I'm sorry, plus or minus, and
Plus
then
or minus.
the z star.
And what's z star?
I forgot what it was for the 99. There it is. The
Okay.
2.576.
2.576.
And then this is where the square root would come in from.
Well, it goes in somewhere. There's a fraction here. What goes on top?
It's the sigma 0.001.
Excellent. Sigma's on top, 0.001. And then what goes on bottom?
And then would it just be the square root of 1 since we're only dealing with one specimen, or will it be 4?
Neither. It's one specimen, but how many times did you weigh it?
Oh, 8 times.
8 times. We got sigma because the instructions up above said that the information that they were giving us was for problem 16.12 through problem 16.14. And the sigma that we had for 16.12 was 0.01. So we just still have 0.001. And then you do whatever the math is and you get your answer. I mean, at that point, it just, plug in, chug, as we like to say. Does that make sense? We're going to have a few chapters coming up on confidence intervals, but this is the idea of confidence intervals. Confidence interval dinner? Surprise me.
Would you like some?
Surprise me. And surprise my class. They're always like, hey, what do you have today? So surprise me. Okay. So what was I saying? I totally lost my train of thought. Yeah, so are there any questions on confidence intervals? We're going to have a couple, that's what I was saying. We're going to have a couple chapters on these coming up for different situations and whatnot. Hopefully the food, I gotta get rid of this. Hopefully the food comes before class. we don't really vary that much. So it's kind of like, well, we do the same things a lot. Anyways, so that's it for now for confidence intervals. We're going to start moving on now to chapter 17, which is hypothesis testing. And we're not going to do much of 17 because first of all, I haven't put up your homework yet for confidence intervals, and I certainly want you to do that before we get really into this stuff. But I do want to start a little bit on it. Okay, so the question is, what exactly is a hypothesis test? Okay. Quite often either in the real world or in science in general, people make claims about something that they believe. So for example, I believe that LeBron James is a 70% free throw shooter. You know, so we're in basketball, right? We had the, we do the free throws and we say he's a 70% free throw shooter. So I have this claim, I have this belief, I have this hypothesis that LeBron James is a 70% free throw shooter. And someone comes along and says, well, I've watched him play for a number of years, and I'm not saying he's a bad player, but I don't believe he's a 70% free throw shooter. They have an alternative hypothesis. Now, how do you test one hypothesis versus another hypothesis? How do we figure out whether one of them is correct or not? So the first answer is you can't. You can never figure out which one's correct or not, because the only way to test hypotheses are by taking samples. And samples, by their very nature, don't give us all of the data possible. But what we have is the following. We have what's called the null hypothesis, and then we have what we're going to call the alternative hypothesis. Some books use the notation HA, like ours does. Some books use the notation H1, H0, and H1. I will probably, without even realizing it, use both interchangeably, just because I'm so used to both of them. But in theory, one is used in the book, one is not, but you're going to see both. In our case, null, so the null is written as H0, and it's if I was going to say this out, I would call it H0, N-O-U-G-H-T. It is called the null hypothesis. It's essentially what you believe going into the experiment without actually doing the experiment or questioning it. So all along, people have been saying, no, LeBron's 70% free throw shooter. He's a 70% free throw shooter. So that's the null hypothesis. That's the status quo. That's what we're testing against. And what we do is we have an alternative hypothesis. We believe it's not 70%. Or maybe it's greater. Or maybe I think he sucks and it's really less than that. The null hypothesis always has an equal sign. There is no exception to that. Something equals something else. The alternative has three possibilities. What are the three ways that two things cannot be equal? If I say the first A, let's say, is equal to B, what are three alternatives besides equal? If I want to compare two quantities and you say they're equal, and I say, no, they're not equal, what are three other things that I can say instead of equals?
Could it be greater than, less than, or equal to?
Well, greater than and less than, sure, but equal to is what we started with. We want three other possibilities besides equals to. Greater than and less than are two of them. There's the third one.
Is it not equal to?
Yes, excellent. Or not equal to. I'm not sure if that's what you meant, Sydney, when you said not at all. It sounds like it was, yeah. So there's three possibilities. Either you say, no, it's less than, or you say, no, it's greater than, or you say, no, it's not equal to. We call this a two-sided hypothesis test because whether it's bigger or smaller, it's not equal to. Whereas these two here are what we call one-sided hypothesis tests. All right, these are one-sided hypothesis tests. And this one here is a two-sided hypothesis test. And what you have in these cases is, for example, let's, instead of doing a LeBron case, let's do another example. You ever eat at Subway? So if you eat at Subway, they claim that their couple minutes. What a tease. They claim that their sandwiches are 12 inches long, right? Are foot-long sandwiches. Hold on, someone texted. greater than less than one, not one hypothesis test, one-sided hypothesis test versus a two-sided, right? One side or, hey, cool. One side or two sides, right? A one-sided hypothesis test or a two-sided hypothesis test. So let's go to, let's do a Subway, for example, right? You go into Subway and you say, hey, I heard that your sandwiches are 12 inches long. I heard that the average length of all of your sandwiches are 12 inches long. And you go ahead and you actually test a bunch. And after testing, you took, like, let's say 10 sandwiches, and all of them were less than 12 inches long. What would your alternative hypothesis to Subway be in that situation if, after looking at 12 sandwiches, every single one of them was less, you don't say less than the null hypothesis, but you say my alternative hypothesis is that mu, whatever it is really less than 12. You wouldn't say, oh, based upon my observations, I think mu is really greater than 12. That makes no sense, right? But you can say less, you can say not equal to. But I think in this case, you might come along and say, you know what? I really think that it's less than 12. So what we do then is we perform a hypothesis test. We're going to test to see whether or not we want to keep the null hypothesis, or whether or not we want to reject the null hypothesis in favor of the alternative. Your two options are either to reject the null hypothesis in favor of the alternative, either reject H naught, or don't reject H naught. We never accept the alternative, ever. We always either reject or do not reject the null hypothesis. Those are the two options. Do we reject the null hypothesis or do we not reject the null hypothesis? It's kind of like when you go to court, or you see people in court. We never say we find the defendant innocent. Nobody ever finds anyone innocent. What do they find? If they don't find them guilty, what do they find? Not guilty. It's all about guilt, right? You can't say we find him innocent. We just say we can't find him guilty. But you're not saying he is innocent, or she. You're just saying not guilty. The same thing here. We can never say, we're going to accept the alternative. It's either we reject the null hypothesis or we do not reject the null hypothesis. Those are the two options. So what will make us decide to reject the null hypothesis? Well, I'll take a sample. And if my sample has an average that's less than 12, does that mean automatically that I would like to reject the null hypothesis? Would that be your conclusion? If you take a sample and your sample average is less than 12, would you automatically reject the null hypothesis in this case?
Yes, because it's not equal to 12.
Okay, so let's say your sample was 11.9999995 inches. Would you say there's no chance that the true average is 12? Would that be your conclusion? Remember, you're only taking a sample, right? There's lots of sandwiches that you haven't tested. Your sample is only a small portion of the population. So if you got a sample that was 11.99995, would you say, based upon your sample, there's no chance in hell that the true value is 12? Would that be the conclusion that you would make? No, because your value is close enough to 12 that, listen, it's a sample. Some are more, some are less. I was close. Yeah, it's certainly reasonable that it could be 12. Now, if your sample was 10.999995, a sample of, let's say, 100 of them, then I might start thinking, you know what? I think 11 is more of an appropriate value, and it's probably less than 12. And I might think about rejecting the null hypothesis in that case. So it's all about, well, no, margin of errors for confidence intervals. Hypothesis testing is a different approach. So there's two different approaches here. Margin of error is for confidence intervals, and I'm building up the idea of a hypothesis test and how to do it. We're not there yet. It's going to take, the whole chapter is just giving us the basics for it. 16 and 17 are the basics for confidence intervals and hypothesis testing, and then we'll get into them in depth and look at all the different situations. Okay, so I'm trying to build up to it. The point is that there is some number that on one side of that number we say, yeah, I'm going to reject the null hypothesis. And on the other side of that number, we say, no, I'm not going to reject the null hypothesis. Our goal is to figure out, not necessarily that number, but our goal is to figure out a method by which we can take our sample and decide whether or not we want to reject the null hypothesis or whether we're not going to reject the null hypothesis. And let's start with going through an example that the book does, just because that way we can see it inside. So here, I'm a good free, you know what, this is crazy. I was going to do a different example. I didn't even know this was here, but this is amazing. Okay, I'm a good free throw shooter. I claim that I make 75% of my basketball free throws. So my null hypothesis, my null hypothesis in this case is that I make 75%, that the proportion of shots that I make is 0.75. I make 75% of my free throws. To test my claim, you ask me to find. You say, you think you're 75%? Okay, go ahead and shoot 20 free throws. So I do a sample and I have n equals 20. I take 20 trials. And I only made 8 of them. So what is my actual proportion? P is my theoretical proportion. P hat is my actual proportion. In the case of making 8 out of 20, what is my actual proportion? What fraction of shots did I make if I made 8 out of 20?
0.4.
0.4, 40% chance. So the question is, if somebody claimed that they made 75% and they only made 40%, I would be very inclined to come along and say, you know what? I think that your actual true proportion is what in compared to 75%? Would you say, I think it's really less? I think it's really more? What would you say in this case if you made 8 out of 20? It's probably less. My alternative hypothesis is that in reality, it's less than. Okay, seems like a reasonable hypothesis, correct? So let's actually figure it out then. How do we do this? So we're going to learn the method that we're going to do it, but I'm going to go ahead and just load up. I know you don't have Crunch It, but I am going to load up Crunch It just so that you can see what Crunch It would do here. I gotta share again. Hold on. How do I find Crunch It?
I have a quick question.
Yeah, go ahead.
So P is what you think that you're gonna make. That's what do you call regular P?
What is that?
Chicken shawarma.
Chicken shawarma. And Three Musketeers.
That's dessert.
I'm teaching class.
That's dessert.
I'm teaching class.
That's dessert.
Go away. Sorry, what were you saying? I got distracted by someone. What was that? Say that again.
Wait, so what's the difference between P and P hat again? One more time.
Okay, so P is the true proportion that I'm looking for, that I do not know, right? I do not know P, correct? I will never know P. P hat is the one that came from my sample. Does that make sense? So what I'm going to do is I'm going to take my sample, and from my sample, I'm going to try to determine how likely it was that I got the result that I did if the true P was really 0.75. Okay, I know the drill. Hold on, I'll explain it again. Just you guys want to see it. You guys, just how do I spotlight this? Did that make sense, by the way?
Yes, thank you.
Okay.
Just use your document camera to show your food.
My document camera is still not hooked up yet. I'm working on that. But I don't know. Can you guys see this? Ooh. So this is my chicken shawarma, which sounds interesting, and lox and bagels, and Three Musketeers, and AW root beer. Sorry. I'm never gonna lose this. Anyways, okay. So let's load up Crunch It. I gotta find it here. Hold on. What's wrong with the screen? 1 second, guys. I got. No, that didn't do it. Remove all pinned. Yes, remove all pinned videos. Okay. Okay. Food review. What's here? That's funny. How do I? Hold on. How do I do this? I lost the ability to share my screen. I don't know where it went. So this method we're about to do will tell us whether
You're sharing your screen right now. Actually, we can see it.
you can see my screen. So you see what's behind it right now? You see this?
Yeah, I see we see the textbook.
Oh, okay, good. So let's.
Yeah.
So I'm gonna go and I'm gonna load up Crunch It. Okay, thank you. Okay. So I can remove this because I don't need it. New. Okay, so what we're gonna do is as follows. Yes, so Sydney, the method we're about to do will tell us whether or not to reject or not reject the null hypothesis. I'm gonna go to statistics. I'm gonna go to Z. I'm gonna go to one sample. And we see here, we have hypothesis test. So this one was it a two-sided? Was it a less than, or was it a greater than hypothesis test? This is one-sided because remember, the claim was, in fact, we could put it here. The claim was, actually, this is a proportion, not a, okay. The claim was that the true proportion was 75%, right? That's your claim. You come along and say, you know what? I think it's really less than that. So the null hypothesis, the underlying belief is that it's really 0.75. And you come along and say, you know what? I do not think it's 0.75. I actually think it's less than 0.75. Now, how many trials did we run? How many shots did we take? 20. How many successes were there? Eight. Excellent. Okay. And then we can calculate. So let's see what we have here. The null hypothesis is that the proportion is equal to 0.75. Correct? You agree? Yes, no, maybe so? Yes. The alternative hypothesis is that P is less than 0.75, correct? Number of trials, 20. Successes, 8. P hat, which is the proportion that I actually got, was 40%. Let's ignore this for a second. Let's ignore this for a second. We're going to focus on the p-value. The p-value is the simplest way of determining whether or not what you ended up with is in any way consistent with the null hypothesis. So here's what it is. If the null hypothesis were really true, then this is the likelihood that this would have happened. Okay, if the null hypothesis is really that p is equal to 0.75, there is a 0.00015 chance that you would have gotten this result. This is less than one. This is about 1.5 hundredth of a percent. Okay, this is 1.5 hundredths of a percent. Is that a high likelihood or a low likelihood? It's so low that if it happens, you have to start questioning whether this is really true. The p-value represents the likelihood. Let me write it out here. The p-value is the likelihood there's got to be a way to do this better. The p value is excuse me is the likelihood of getting the result you actually got, or something even less likely, or even more extreme, better words, more extreme, if the null hypothesis were really true. Let's erase all this nonsense. And let's go ahead. Well, I don't know how to move that, but okay. So the p-value is the likelihood of getting the result that you got, or something even more extreme, if the null hypothesis were really true. So if there is a 1.5 in 100th of a percent chance of getting this result with the null hypothesis being true, and you actually got that result, you got to start questioning whether this is true or not. Right? Something so unlikely to occur. Essentially, it's like 1 in a million. And it actually happened? Dude, you're not really a 75% free throw shooter. I'm going to reject the null hypothesis. Does that make sense? Anyone following?
I have a question. So
Yeah.
basically the p-value, or the p-value basically means like it's the chance of it actually happening.
If the null hypothesis were really true.
Oh, so basically going off the hypothesis, saying that the hypothesis is true. Right?
Yes, it's all about this guy. Okay, the null hypothesis is that, not the chance the null hypothesis is true. It's the chance of getting what you got if the null hypothesis were true. If the null hypothesis were really 0.75, there is such a tiny chance of getting this result. And you got that result, this can't be true. That's essentially the logic behind it. If it were true, you shouldn't have gotten that result. Therefore, it's not true. Or therefore, I'm going to conclude, based upon my data, that it's not true. Does that make sense?
Yes.
Yes, it's the chance of getting the actual value that you got, or something even more extreme, if the null hypothesis were really true. So in this case, there's a 0.000150 chance of getting 0.4 or something even less than 0.4. More extreme from 0.75. So the chance of getting what you got or something even more unlikely, more extreme, more to the left is so small that I really don't think this is valid. That's the idea of hypothesis testing. What we do in hypothesis testing is we have the null hypothesis, you have the alternative, you take a sample, you compute your p-value, and we're going to learn how to compute the p-value, but you compute the p-value, and then you look at the p-value and you say, this is a chance of me getting what I got. Do I want to, or do I, when I look at this number, do I conclude that the null hypothesis is most likely incorrect because this p-value is really small? Or do I say, okay, it's large enough that it's certainly a reasonable result, if not expected. Let me do one of the other sorts. Let's do this example right here, because I did it in my last class, so I know it'll be a more, it'll be an example with a different outcome. So Diet Colas usually use artificial sweeteners instead of, to avoid sugar. Yes, it's very important. In all of hypothesis testing, you always assume the null hypothesis is true. Always. And everything you do is based upon that fact, so that your result is based upon that fact. And then when your result is so unlikely, we say it must be that that fact that we're assuming is actually incorrect. That's the logic behind it. Everything is based upon the null hypothesis being true. So in this case, we have Diet Colas. They use artificial sweeteners, and sweeteners gradually lose their sweetness over time. That's just a fact. So when manufacturers test new colas, they test for loss of sweetness before marketing them. And what they do is trained tasters actually sip the cola and score the cola on a sweetness score of 1 to 10. Larger scores, more sweetness. They then store the cola at high temperatures for a month to imitate the effect of 4-month storage at room temperature. And then the tasters come back and taste them again. And what we do in this example, at least, is we look at the difference between the before and after. The bigger the difference, the more sweetness was lost according to that taster. So suppose that we know that the sweetness loss scores vary from taster to taster according to a normal distribution with a standard deviation of sigma equals 0.1. Now remember, two of the things that we need are normal and known sigma. So they just gave us that. It comes from a normal and sigma is equal to 1. And here are the 10 results, 1.6, 0.4, 0.5, and so on. Now, the average sweetness loss in this sample is x bar equals 0.3. That means the average before minus after is 0.3. The question is that good evidence that the cola actually lost sweetness? We're testing to see whether or not the cola lost sweetness. So the null hypothesis always gets the equal sign. So what exactly in this case are we testing against? What are we testing to see if it's true? We're testing, yes, exactly. We're testing loss of sweetness, which means if there's no loss of sweetness, mu should be equal to 0. And if there is a loss of sweetness, mu should be greater than 0. So we have a one-sided test where we are testing against the null hypothesis, where no sweetness is lost, that the difference is 0, against the alternative where mu is greater than 0. And we have our x bar is equal to 0.3. We have our sample size is equal to 10. We're told sigma is equal to 1. And we want to test this. So what we're going to do is we are going to go to crunch it. And we're going to test this case on crunch it. So crunch it gave me my 10 values right here. I'm going to go statistics, Z, 1 sample. We have hypothesis test. What is the mean under the null hypothesis? What is the mean under the null hypothesis? 0. What is the standard deviation? What does OPE stand for? One. Is it two-sided, a less than, or a greater than? It is greater than. Do I want to use a column of data for my sample? And if so, which column should I use? So this is my sample data, right? Labeled by the loss. And then I say calculate. So null hypothesis is that the mean is 0. Alternative hypothesis, the mean is greater than 0. Sample size is 10. Sample mean is 0.3. Deviation is 1. Ignore this for now. We'll get to it later. And my p-value is 0.1714. That means that there is a 17% chance that I got this result, or something even more extreme from 0, if the null hypothesis is true. Now, yes, exactly. We do not reject it. 17%. I'm not going to claim that something with a 17% chance is going to happen every time. But if it does happen, you don't sit there in stunned silence and say, how could this have happened? 17%, that's crazy. 17% is like flipping a die and rolling a 1. Okay, if I say, if it's a 1, I'll give you $10. You don't expect for a 1 to occur, but if it happens, you're not shocked. It's certainly within the realm of possibility and plausibility. So the idea is that if the p-value is high enough, we do not reject the null hypothesis. And if the p-value is low enough, then we do reject the null hypothesis. And the question is, what is that number where above it we reject or not reject, and beneath it we do reject? And the answer is, as a general rule, 5%. Unless you're told to use a different p-value in the problem, assume that the cutoff is 5%. So if the p-value is less than 5%, it's less than 5% likely to have occurred, we reject the null hypothesis. If the p-value is bigger than 5%, like it is here, we do not reject the null hypothesis. We will learn about Z statistics later. This is just the p-value approach. The Z statistic approach is a different approach for coming to the same conclusion. So are there any questions so far on the basics of hypothesis testing? Is there another website to do the thing? Well, let's take a look. Hypothesis testing calculator. Am I still sharing? Hold on, I don't think I am. 1 second. Hypothesis testing calculator. So let's go to the first one. This is a t-test. I don't want a t-test. We're doing z-tests. So let's go back and do Z hypothesis testing calculator. Here we go. One-tailed or two-tailed. This is one-tailed. Significance level is 5%. That's the cutoff. Sample size is 10. Sample mean is 0.3. Population variance was 1. Population mean is assumed to be 0. And I think that's it. So here we go. The value of P is 0.17106. Is that what we got in the Crunchit one? 0.17, close enough. Rounding errors. Right? 0.3, 1, 0, 10, 5%, one-tailed. I think z-score 0.94868, 0.94868, close enough. So yeah, so that was the very first link, right? So you see that there's always ways of doing these things online, right? Everything's online. Google goes down. I don't know what I would do. I'd have to Google something to see how to find it. That was funny because, you know, never mind. Okay, so are there any questions on this? All right, I will put up homeworks 15, 16, which are just basic. I should have done it a few days ago. I apologize for not. I extended 8, so I'll give you a little more time for that one. But I'll put up 15 or 16. We only did the bare bones of 17, so we didn't really get into it too much. We will go over it next time and expand upon it. And then after that, we will spend some classes looking at all the different ways of getting confidence intervals and all the different types of getting hypothesis tests. There's like 8 or 9 of each. In this situation, use this formula. In this situation, use this formula. In this situation, use this formula. Of course, they're all online. You just got to find the right links and we'll go from there. So unless there's any other questions, I'm going to start my vacation 23 minutes early or 33 minutes early. Give you guys a little break so I can finish my mediocre dinner. I do not recommend getting these chicken shawarma. It's not worth. I eat it anyways because I can't stop eating, but all right, everyone. By the way, someone told me about this thing called Dippin' Dots. You ever hear of them?
Yes.
Are they as good as everyone said they are? They're the best?
Yes, they're the
It
best.
used to be.
All right, so everyone's like, thank you, Richard. Okay, so everyone's saying they're good. Okay, so Dippin' Dots, I'll have to get them this weekend somewhere. Make sure they are in dry ice.
Go to 7-Eleven, they have them.
7-Eleven has them? All right, I'll get like one of each. So that'll last me like 5 minutes. Oh, banana splits. Oh, banana split. You stop. Don't even say anything else. Banana split. That's it. I love my banana splits. They're so good. Anyways, get lost. Have a good vacation. Or at least I will. I'll see you guys next week. And I'll have everything graded because now I'm on vacation. I can do it now. Yay. I will. I'm trying. I have no high school for the next 10 days till the Monday following. That's really nice. So my days are mostly free. Of course, I'll be grading papers the entire time because I have like 1,000 to grade. But I'll get them done. I promise. I promise. All right, guys. Have a good night. See you guys soon. All right. All right.
Hey, Professor.
Yeah.
This is Anthony. I emailed you on the test day and yesterday about the test. I just wanted to see if you saw my emails or not.
Yeah.
Yeah?
I did. Don't worry about it. You got it to me. I'll grade it. You'll be okay.
Thank you so much. I appreciate it.
Oh, no problem, man.
Have a good one.
You too. Still recording.